Hey folks, I had a few homework questions here on the Unit 4 homework questions Jamboard, and I thought I would just make a video because I wasn't sure who had asked them, but it wasn't people who were in cohort B in class the last day or two. So I'm just going to go through and post this video along with the solutions. So here we've got the limit as x approaches 2 pi of this this function, and we don't actually have any indeterminate form. We can just do a direct substitution. So this is going to be 2 pi cubed plus pi squared times 2 pi minus 5 pi cubed. So we have to make sure we're careful to cube that whole 2 pi, so it's 8 pi cubed plus, and this will be 2 pi cubed minus 5 pi cubed, and then 8 plus 2 take away 5, we've got 5 pi cubed. It is a little bit weird to have pi squared or pi cubed, but you can just solve that directly by substitution. Here as well, we've got the limit as x approaches -3, and it kind of feels like we're going to get like a negative value in a square root, so that might be a problem. But let's just try subbing it in because I think it's actually going to work out okay. So we get -3 minus 3 over 2 times -3 plus 4. So we get the square root of -6 over -6 plus 4 is -2. So we actually just get root 3. So both of these can be solved just with direct substitution. The next two are limits, I think, from the same section of homework. These are a little trickier, and we are going to have to do a bit of manipulation here. We would get an indeterminate form for C. If we just sub that in, we would get 0 over 0, so we need to do some work. So this is going to be, keeping the limit notation is important here, and we have a difference of cubes in the numerator. So that's x minus 3 times x squared plus 3x plus 9 over x minus 3. And then this can reduce top and bottom. I do like to show rewriting this out, the limit as x approaches 3, because now we have something that we can substitute into that will not be an indeterminate form. Then when you actually sub in that value, that's when you drop the limit notation. So we have 9 plus 9 plus 9, which is 27. For E as well, in this question number 7, we have an indeterminate form. So on the numerator, we'd have square root of 4 minus 2, which is 0, and the denominator 4 minus 4. So I can't do just a direct substitution in there. I would encourage you, whenever you see radicals in your limits, to look at doing multiplication by the conjugate. So I'm going to multiply top and bottom here by root x plus 2 and root x minus, or plus 2. Whoa, same top and bottom. So in the numerator, keeping your limit notation, limit as x approaches 4, we're going to, basically this is like a difference of squares. So when we FOIL this out, I'm going to show this step, but you definitely don't have to, especially once you get confident with it. Root x times root x is just x. Then I would have plus 2 root x and minus 2 root x. It's a terrible square root sign. And then minus 4 all over x minus 4, and I'm not going to distribute this in, but you'll see that when you multiply by the conjugate, that's the whole point of the conjugate, to get those middle two terms to cancel out. So you would have the limit as x approaches 4 with an x minus 4 on top and x minus 4 times root x plus 2 on the bottom. Now this, of course, can reduce top and bottom with the x minus 4. Please don't forget that you still have a numerator of 1 Sometimes that's surprisingly common for people to forget that and kind of like let their denominator float to the top because they don't have anything left. So we've got 1 over root x plus 2. This is something you can take the limit of now. So I'm going to drop the limit notation and just say that's 1 over square root of 4 plus 2, which is 1/4. This one I took up in a Google Meet at lunchtime today, and I will post the video from that Google Meet. I think it recorded properly, so I will post the video from that Google Meet. This is a very big example of multiplying by conjugates and kind of doing 2 different conjugates, one for top and bottom. Okay, here we're looking at a piecewise function. So we see that f of x is equal to 4x if x is greater than or equal to 1/2. So I'm just going to set up a sketch here. So my function for x is greater than or equal to 1/2. So I would say that f at 1/2 is 4 times 1/2, which is 2. So I would have a point there. And then this is going to equal 4x. So it's going to have a line with a slope of 4. So it would go like that, upwards. Kind of hard to draw straight enough. Upwards like that. Pretending that's a little bit straighter than it is. Okay. And then the next piece is that f of x is 1 over x if x is less than 1/2. So let's just kind of figure out where the open circle would be. 1 over 1/2 is also equal to 2. So for this part of the function, I would have a whole at 1/2 and 2. So that means it is actually continuous. And then this is going to be the 1 over x function. So this is going to go super steep up there to an asymptote. And then I guess it would be there. You'd have the whole negative side of that function. But they do meet up. You do end up getting the limit the same from both sides. So if you were evaluating the limit as x approaches 1/2 from the left of f of x, that would be using the blue function, the rational function there. So I would say that's 1 over 1/2, which is 2. And the limit as x approaches 1/2 from the right of f of x, now you're going to use the 4x, which is also 2. So because the limit as x approaches 1/2 from the left of my function equals the limit as x approaches 1/2 from the right of my function, we know that the general limit as x approaches 1/2 of my function is 2. So you would evaluate the 2 different sided limits there and come out with equal values. So that means the limit exists, even though, even if it was discontinuous, but it's not there. Okay, we've got 27 minus x over x to the 1/3 minus 3. Now, typically, whenever we have something that's not just a square root, you're going to want to do substitution. So I'm going to say let u equal x to the 1/3, because that's kind of the piece of this that I don't really want to deal with. That would mean that x equals u cubed, right? Cubing both sides. And I know as x approaches 27, u is going to approach 3 because u is x to the 1/3. So once I kind of list out all of this information up here, I can rewrite this limit as the limit as u approaches 3 of 27 minus u cubed over u minus 3. And then I can factor. Now I see that this is kind of like the backwards order. I might factor out a -1 right off the bat there and then make it u minus 3 difference of cubes, just kind of swapping the order around. You don't have to. You could make it 3 minus u, but then you're going to have to factor out a -1 later. So then I get u squared plus 3u plus 9 over u minus 3. And we can reduce our u minus 3's, which were giving us the trouble of that indeterminate form. So this is the limit as u approaches 3 of -1 times u squared plus 3u plus 9. Now we can substitute this in. -1 times 3 squared plus 3 times 3 plus 9, and that's -27. This one is a little bit tricky. We have to kind of think about the absolute value function and sort of what that means. So we want to know if the limit as x approaches 1 of this function exists. So I want to think just a little bit about the absolute value of, absolute value, the absolute value of x minus 1. So if x is greater than 1, then the stuff in the absolute value would be positive. So this x minus 1, so then x minus 1 would be greater than 0, and the absolute value signs don't do anything. So if x is greater than 1, that means the absolute value of x minus 1 for those points equals just x minus 1. The absolute value doesn't change anything. On the other hand, if x is less than 1, then x minus 1 is negative. Then the absolute value signs have to change the sign. So they change the sign of what's inside that x minus 1 inside. So for x less than 1, the absolute value of x minus 1 is actually equal to negative of x minus 1. So it multiplies it by a negative to change the sign in there, because the x minus 1 would be negative, so you need to put a negative in front to make it a positive. So I might rewrite this as a piecewise function and say for x greater than 1, the absolute value signs aren't doing anything. X squared plus the absolute value of x minus 1 minus 1 over the absolute value of x minus 1 is just equal to x squared plus x minus 1 over x minus 1. Those absolute value signs were doing nothing. So then this would be x squared plus x minus 2 over x minus 1. And we can simplify this to x minus 1 x plus 2 over x minus 1. So these guys will reduce and we just have x plus 2. So from the left, this limit is just equal to x plus 2. For other values, so for x less than, less than 1, we know that the opposite would be true, that this absolute value sign is changing the sign. So then x squared plus the absolute value of x minus 1 minus 1 over the absolute value of x minus 1, we would actually need a negative sign in there. So it would be negative x minus 1 over negative x minus 1. Multiplying that in, collect like terms, I get x squared minus x plus 1 minus 1 over negative x minus 1. So here I get x squared minus x, and I can common factor an x on top, and I end up getting that that's equal to negative x. So I'm running a little short on room here, but I think I can squish it in. So if I take the limit as x approaches 1 from the right, so from bigger numbers, I'm going to be looking at this x plus 2. It would be x plus 2. So then the limit there would equal 1 plus 2, which is 3. And from the left, I'd have the limit as x approaches 1 from the left of this original function, of that big messy thing. It actually simplifies to just negative x. So that would be negative 1. So the limit does not exist because it wouldn't have the same value on each side. And I may just squeeze another board in here. I don't know how to change the background when I'm on my tablet. So my functions were from the right, it was x plus 2, and from the left, it was negative x. So I don't think it was called f at x, but we'll just kind of write it like that. So this is equal to x plus 2 for x greater than 1, and negative x for x less than 1. So that's what the sketch of this would look like. So we've got x as 1. So we know that this would have, I suppose I should draw some semblance of a scale on here. So if this was negative x, that would have an open circle there, and it would go with a slope of negative 1 out that way. And the other one would have an open circle there. Remember that we had that x minus 1 on the bottom, so it's not defined at x equals 1. And it would go like that. So that's kind of what my function would look like, something like that with the absolute values. This one is a really good question. Some of these can be pretty tricky. So here, if I'm looking for the limit as x approaches 2 from below of g at 2 minus x squared. So I want to just, first of all, evaluate the limit as x approaches 2 from below of just 2 minus x squared. What's happening with that? Don't worry about the g function. Just say here, if I'm doing 2 minus x squared, and x is getting closer to 2 from below. Now we know that 2 minus x squared, if you had an x value of 2, you get 2 minus 2 squared, which is 2 minus 4, and that would be negative 2. So it is going closer and closer to negative 2, but it's going closer to negative 2 from a certain side. So here, we want to kind of think about what happens to this x squared. X squared, maybe I'll write this out kind of with better limit notation. So the limit as x approaches 2 from below of just x squared. So the limit of that approaches 4, but it's from below. So this is, imagine you had like 1.999 squared equals, it would kind of be close to 4, but it would be like 3.9 something something, right? It wouldn't be quite 4. It would be a little bit less than 4. Now, if we were thinking subtracting, this is just kind of like thought bubbles here, not necessarily actually part of your solution. So then if we were thinking about subtracting 2 minus this number, so then we're kind of like, okay, that x squared is getting pretty close to 4, but it's a little bit smaller. Then 2 minus x squared would be like negative 1.999. It would get like from that side. So the limit here, as x approaches 2 from below, of 2 minus x squared is, that is negative 2, but it's actually from above. So this is slightly bigger than negative 2. So that's kind of what we're looking at, that the limit as you get close to 2 from below of 2 minus x squared is getting close to negative 2, but it's a bit above negative 2, a bit bigger. So then we're going to look at the limit as x approaches negative 2 from above of g at x, because this thing, this like clump of stuff in the middle, is getting close to this. So we're doing the limit as x approaches this of the outside function g. So then we just look at our graph, and we're going towards negative 2, but we're doing it from numbers above negative 2. So like these negative 1.999. So that would be right around here. It's going close to a value of 0. I also took up page 3312A, a pretty big derivative from first principles, and that's in the other video as well. It was 2-pager, and I think that's it. So if you guys have any other homework questions, please continue to add them into the Jamboard. If you're in a synchronous class, or if you drop in for math help, I will do it in person with you. Otherwise, if it's been a day or so, I will make a video. If you don't make it to an in-person class and you've put something in there, please just send me an email and ask for a quicker explanation too.